Hi, this is Amy, and today I'm going to talk about two independent sample tests. This time, we're going to compare the means of two independent populations, so it is not paired in any way. Each sample is independent. There's two types of these tests: pooled variances kind of sort of the same, and unpooled variance test when they are not equal. Very different. If they're approximately the same, that is good enough. Let's start with the pooled variance t-test. We need two unrelated samples, and their standard deviations and variances are approximately the same. Every time we do a hypothesis test, the central limit theorem must apply. We have a big sample, or both populations are normal. Otherwise, we're going to have to use other methods. So I'm going to write that down. This won't work. Okay. Let's go over the formulas for two independent samples. I'm going to start with the standard deviation or variance we're going to use. What we're going to do is called pooling the variances. And that's the same as averaging them. Because they're approximately the same, we can find a weighted average of the two variances, and then that's what we're going to use. We call that SP squared. The P stands for pool. So basically, we take a weight, subtracting one as a degree of freedom, the way we often do, and then we put this together. So we have our two variances, we dump everything together, we come up with this pooled variance that's going to be in between the two. Then that's what we use on the bottom. That bottom is a standard error, the same way we do in normal hypothesis testing. Now we have a few differences though. We have both ends, that's the number of each population. On the top, we have the differences. So what is the difference between the two populations? We're looking for what that is, and often we're setting that to be 0. If the difference is 0, that means they're the same. So often our null hypothesis will be that they are the same. That makes our alternative hypothesis that they are different. The math works with any number there. It doesn't have to be 0. I could hypothesize that the difference is no bigger than 10. We can do a one-sided test. We can do a two-sided test. We have all the same tools as we normally have. On the top, we put the actual difference minus the hypothesized difference. Then on the bottom, we put that standard error. Okay, are you ready for an example? I sure am. Let's start with an example. At the Huang Manufacturing Company, new employees are expected to attend a 3-day seminar to learn about the company. Management decides to experiment to make it less time. I'm going to put that down at 3 days, and they're going to try out a new method where people watch DVDs. This will only take 2 days. What we need to know is whether or not each method is different. Is the new method better or worse than the old one? Is there any difference at all? So what we're going to do is test whether there's a significant difference in the mean scores of the two groups. Assume that the test scores are normally distributed and the population standard deviations are approximately equal. Why do we need to assume these things? We need to assume that it's normally distributed because we want to use the central limit theorem the same way we always do. That means that we need everything to be approximately normal, which often happens, or we need larger samples. Larger samples are often a better way to go about that. If we had each sample, A and B, was bigger than 30, we would not have a problem. Population standard deviations are approximately equal. We're going to look at this because we can actually find the standard deviations. And when we look at it, they actually are. So I'm going to just click into Excel over here, and we're going to see what we have. To find the mean and the count, all I use is use count, averages, standard deviation. There's a standard deviation command. Square it to find the variance. So over here, this is S, this is N, and this is X bar. I can find all of these things. The truth is 5 and 6 are not very different. It's okay to say that they're the same. Usually, we're just looking at things in the same ballpark. We don't want one that is about 10 times bigger than the other. That would be a problem. So normally it's okay, but what we are going to do is see what will happen whether we assume they're the same or not. So what we're going to do is find a new standard deviation or a new variance. This variance is called a pooled variance, and it is a weighted mean or a weighted average of the two sample variances we have. What we can do is just plug everything in here. So n1 minus 1, 15 minus 1, times the standard deviation squared, plus n2, which is 12 minus 1, times 6 squared. And we take that whole thing by, this is actually our degree of freedom, 15 minus 1 plus 12 minus 1. When we pump this in, we're going to come up with our actual pooled variance, which is 29.84. Of course, we don't need to do this by hand. We can do this using a calculator, a computer, and just putting in the same function into Excel. Let's go back to this. So now we're going to start our hypothesis. Often, mu1 minus mu2 is hypothesized to be 0. That means there's no difference. We already talked about this one. And that's what we're going to do here. Here, our null hypothesis is going to be there is no difference between training methods. That means the alternative is there is a difference. If there is a difference, then it matters which one we choose, and we choose the one that's better. If there's no difference, we are allowed to choose the one that's cheaper. That's the 2-day training as opposed to the 3-day. So this is our hypothesis, and then we would go and look everything up. Our degree of freedom over here is that same denominator below, 15 minus 1 plus 12 minus 1. That's also all of the data points we have minus 2 for 2 variable. We can do this as well, and then we look up in the t table what our critical value is. So our t critical turns out to be 2.05, let's say 60. Let's round. If we didn't have a t table, again, I'm going to say that is built into most computer programs. We can just look that up. So what are we going to do? We're going to write this in, and we're going to say 2.060, that's a plus minus, and negative 2.060. Let's put in our critical area. So I'm going to reject if the test statistic is less than negative 2.060 or if it's greater than 2.060, if it's in either of those regions. Now all we have to do is find the test statistic. Again, mu1 minus mu2 is 0. So we can just plug 0 in there. So we end up with the difference of the two means, which is 48 minus 57 over the square root of that pulled variance we got, 29.84, and we have 1 over 15 plus 1 over 12. Again, we can put that through a calculator to get negative 4.254. Another way to do this is to just use this exact formula we have to come up with the answer using Excel. So what do we have? Let's put that in. That's our test statistic. So it's in the rejection zone. So we are going to reject. T-test is less than negative 2.060. So we are going to reject H0 at the 5% level. There is enough evidence to conclude that there is a difference. Now we get to make our business decision. A business decision here would be to use the better method. And in that case, that's going to be the old method because it's the new method because the test scores are higher on that one. So we're looking for what is better here. Now let's look at this again, but instead of assuming that those variances are the same, we are going to assume that they are different. Okay, let's go look at an unpooled version. We're going to do the exact same problem, but this time we're not going to assume that they're pooled. The hard part part of this is definitely the degrees of freedom. It's extreme. It's a very difficult formula to look at, so I don't advise ever doing it by hand. We could, but we don't have to. Over here, notice I put the variance over n because that shows up a lot. I ran this through. It's 21 point something, and we always round down. In Excel, that's the command int, and we come up with that new degree of freedom. So here, our degree of freedom is 21. Always use a computer. We now have a new t-critical. It's not going to be what it was before. In fact, our t-critical is going to be 2.079. And that's because we have a different degree of freedom. When we end up with a different degree of freedom, we have a new critical value. Test, we're just going to jump this through the exact same way we did before and put in what our hypothesized means are. 48 minus 57, that part is still 0. And now, instead of pooling the variances, we're looking at them as separate objects. So S1 is 5 over 15 plus 5 squared over 15, 6 squared over 12. And at the end, what we end up with here is negative 4.166. Putting that on our chart, we end up with the same answer. We're going to reject. So let's look at this data a little more carefully.